Wait, so I'll tell everyone, please, you don't master questions, you just understand principles. When you understand principles, then you master the questions, okay? But if you just master the question, it's impossible to solve most of the questions. But if you, because only when you understand the principle, then you master the question. If the question was ever repeated, meaning you solve it within a short span of time. But when you understand the principle, if something comes with it, you'll be able to solve it. Yeah, so we have that, we have that, we have that, we have that. Okay, so here's how many 3 meters. And here is also 3 meters. So we have the distances, which are 3 meters, then here is what? 2 meters, then here it's also 3 meters. Then of course we have the height until this level, and until the upper apex, this is 4.5 meters. So we're saying we're applying what method? Section method. So section method was the same as our joint method. The first thing what we do, we have to find the reactions, of course, and all the supports which we were able to find. So once I find them, my first step, of course, is finding all the reactions, then I'll be able to label them. So here we are at Ky, which is equals to what?
9.
9 kilonewtons. Then, of course, the AX of what? Eventually it was 0 kilonewtons, which does not quantify for anything. And the EY is equals to what?
7.
7 kilo. So that does not give any problem. So we said now what's interesting is we identify the sections that we're interested in. And it's evident that the sections we're interested in, according to the question, is what? Section or member. So when we say section, so wow, this is very resourceful. Wow, this is resourceful. This is good. Wow.
Is that engineering?
It's evident. This is resourceful. Thank you. Okay, so what is identify your sections or you identify what G what F and what G. What G. So eventually why they call it section method is because if you look at your diagrams, for example, if I look at this number, this is what G and this is what F. So your diagram, if you notice, they are more like roads. Then here you have a connection to the P and the P. So in reality, this has an area which is in the units, which is in square units, so it becomes a section. So in most of your physics programs, you will look at an area as a section. So that section is that member. So we refer to it as a section member. So once you identify this, the members. So that's in our step 2. So once we identify the members, so I can't write step 1, step 2, we've already done that in class. So once we identify that, what do we do is that we have to make a cut. Right? So we have to cut. And that cut will go through the members we're interested in. So what's the first member? It's this one, right?
Yeah.
So I have to cut that member, then cut the other member I'm interested in, and for preference sake, ensure that you cut it straight. It simplifies. So a straight cut, cut through our different members. So once your cut is done, you notice that you've got your left hand side, right? And you've got your what? Right hand side. So you're supposed to choose which part of your truss you are going to work with. Is it the left hand side or is it the right hand side? So the easiest indicator to choose is look at the number of elements you have on your right hand side and look at what you have on your left hand side. So looking at this question, it's preferable that we work with the right hand side. We can also work with this other side, but preferably we can choose the right hand side because it's got fewer elements. So if someone decided to choose the left hand side, so what's happening is that in joint method, what did we say? When you have a joint, we suppose we've got a tension, meaning we're pulling that joint. So this is N. So the same principle applies with the section, meaning at the section you suppose to got also a tension like that. So it's the same principle. So if someone says I want to work with the left hand side, so what that's saying is where I have my cut here, what do I do at this point? I put a pulling force, which is a tension, which will be N, G, F. And here, what is it going to give me? It will be the same thing. It will be what? N, G, D. And here, what is it going to give me? Tension, which is N, C, D. So this will be considered to say I'll have to rub this other part and just remain with this left hand side. So if someone chooses to work with the left hand side, and once they remain with the left hand side, it means you remain with the entire structure. We said we have to consider the entire structure as one. So we just consider all this as the entire structure. While this one, I usually advise instead of rubbing this, I can draw it in just dotted lines. Because the geometry at times will help me calculate the angles. So that's if someone decides to use the left hand side. So we'll apply the principle at the right hand side. So since we've chosen the right hand side, what does it mean for us?
You get the tension.
I'll just redirect my
Forces.
my internal forces, of my tensions, which I'm not sure if the tensions or compression, but after calculation is verified. So I'll decide, say this will be what? In that direction, this will be my N. It can be F, G, or J, if it's the same thing. So in here also, you can say just NGG, and here, the other side will be what? NC. So what has happened is I've chosen to work with my right hand side. So once I choose my right hand side, so what happens for this? Instead of me rubbing them, normally I can rub them off. I can just consider to say they are more dotted lines. The only thing I need from them is mostly geometry for necessary. So they're not complete lines. So this part of the structure is not really so important to me. But what is important for me, this part of the structure is only geometry. When I say geometry, it means just its dimensions, like 3, like this 3 or this 9. But the forces don't exist. So it's more like they don't exist. So the only focus, it's more, in other sense, others would say, well, since I'm choosing my right hand side, I will, let me just do it. I'll actually rub the other part of the structure. It's not necessary for my structure. So that's the advantage. As long as I know I have that. But when I wrap the other part of the structure, you've noticed that I've left a certain portion, right? I've left the whole element. Why? It's because all this will help me calculate my angle. So here I have, what was the distance? Up to here, here is what? 3. And here is what? 2.5. Until then, I'll need that geometry. Then what else do I need? Then this force here, since it's not part of my cut is here. What happens is I also don't need the force. So I find that things become a bit more simplified. So I just rub that, you don't really need it. Then from there, I have to consider the whole thing as more of one structure. So the first thing you identify is, you see that this is inclined, right? So you identify to say, this is my what? My X positive. Then this is my what? My Y positive. So what you're having is, at each and every joint, you can just identify to say, so it's the same as this would be my Y positive, at this joint, this would be my X positive. Same applies at this, right? And this will be my y positive, this will be my what? My x positive. Why am I doing that? Is because when you have a joint, what do you do? Draw straight lines like that, because those straight lines help you identify your angles. This is f, so this means here you have an angle to be theta what? Theta f. This is also inclined, so it means at this point here you have an angle to be, this is point D, so you have theta D. So you have to evaluate those angles. So when you want to evaluate these angles, the first thing you have to look at is, do I have right angled triangles? So for example, for this one, that's why I left point C. Why? Because I know it gives me a right angled triangle until this point, which is 4.5 meters. So meaning my theta D is equal to what? The tangent of minus 1 of what? 4.5 divided by 3. So meaning my theta D is equal to what?
56.3.
Is equal to 56.31.
3099.
So 31 degrees. So to two decimal places. So here I know I'm having what? 56.31 degrees. So that will help me. So that will help me to have my angles. Actually, my force be projected in both my positive axis. Then the other one is what? Theta f. So theta f will be equal to what? We can identify a right angle triangle, right? So it will give us what? Here we have a distance. What's the distance? 1.5. So it will just give us tan minus 1 of 1.5 of 1.5 over what? 3, which gives us what? 26.1?
57.
57. So this will be our 26.57. So that's really important. So once you do that, you're almost done solving the problem. So once you do that, you are almost done. So once you do that, you can now look at saying, okay, what we'll do is that since these are inclined, you can actually now project them in your different references that you have defined, positive references. So the easiest, of course, is at D, right? So at D, we have, this is our x positive, right? And this is our y positive. And this is our n GD, right? So now, once I find that, I can just say my NGD is acting at a point D. So that gets simplified. Then from there, we also have, let's not forget, we have this, what's this? NCD. And never forget the force that's acting there. Then here, what's the angle? 56.31 degrees. Okay, so our projection, I'm sure by now you've understood it. So the idea of the projection is that, for example, if I have 2 kilonewtons here, right? And I have an angle of what? Of 30 degrees here. So what happens, this is the start and this is the end, right? The start of the vector and the end of the vector. So meaning for me to go towards the end or to reach this final position, what do? I have to move in this direction, right? Then I have to go upwards in this direction. So this is maybe the y and this is the x. And of course we'll say this is the x positive, and of course we can say this is the y positive. So meaning I can simply apply what? SOHCAHTOA. So if I apply SOHCAHTOA on this problem, what do I get? I just get my cos 30 is equals to my adjacent, which is x, over my 2, and I'll eventually get x is equals to what? 2 cos 30 degrees. As simple as that. So that's the idea of the projection. And this was in a positive direction, so it's in a positive direction. If it was negative, I have a negative here. So it's the same thing that applies here. So if it applies here, you have NGD. So for your NGD, of course, you will get your projection. So I can quickly write it. You can, because this here will be the same as this here, right? Then this here will be the same as this here, and this will be the same angle as that there. So meaning I put NGD, and this NGD is going upward, so it will just give us sine 56.31, and here downward is going in the negative direction. So adding to this, that's there, it will simply give me my NGD with a negative cos of 56.31 degrees. That's what I will get. I'm sure there's a class in here. I'm sure there'll be a class in here. So we'll get something like that. So you have to reapply it for the other point, you apply it for this point.
Someone to close.
Yeah.
Having a class.
Huh?
Yeah, we are
Also
in
having
class.
a class.
Someone goes. Just a minute. Excuse me, you're supposed to have the class again? Oh, right now.
We're also having a class
We also in
right now.
Okay, so I think we've understood up to there, right?
Yes.
So we'll apply the same principle up there, right? Yes, then. So we can cut from here, then we have to continue. Let's not disturb people who are having their class.